Hello. Today, we're going to be going over the definition of a derivative and the limit process to find a derivative. So first, let's define a derivative. Let's imagine I have some function, right? Let's say it's x cubed, f of x equals x cubed. So a derivative is going to help us find the slope of a tangent line at any point on this function. So what do I mean by tangent line? So let's think back to circular geometry. So this is a tangent line. It touches our circle once and then continues off. So it's the same with our function. Let's pick any point. Let's say here, point A. Tangent line to this function. It's going to go like this. Touches our function just once. And that's it. And basically what it tells us is the slope or instantaneous rate of change at our point, which is A. So let's now have 2 points. Let's use f of x is x squared to show this. So we have 2 points, A and B. Okay, let's call this horizontal distance just x. And let's call this distance h. Okay, which means this y value is f of x. This y value is f of x plus h. Why is it x plus h? Well, we find this whole distance has to be the sum of x and h. And we plug that into our function, we get our output, which is our y. So how would you regularly find the slope between these 2 points, right? Well, we would do the slope formula, which is y2 minus y1 over x2 minus x1 is equal to m. M is slope. So how can we manipulate this to fit our example with x's and h's? So we can rewrite this as this. So this works because f of x plus h is the first y value. F of x is our second y value, lower y value. X plus h is our bigger x value, or x2, and our x1 is just x. So we can simplify the denominator here, and we are left with, on the denominator, just h. So how does this help us in finding the rate of change, though? So let's imagine we have this line again between these 2 points. Let's say I want to find the slope at just A, not between A and B, but just at A. Let's pick a third point, C. Now C is much closer to A, and if we notice, C is a smaller distance. Let's call this K. Okay. So instead of calling it K, what if we just call it a smaller value of H, right? Let's say H goes from 2 to 0.5 at point C. Okay. Not exact, but let's just say that. So this line between A and C, we can draw it, is different, right? It's getting us closer to our tangent line at point A. Now let's imagine we picked a point even closer to A with an even smaller value of H. We can get closer and closer to A, to where we have an instantaneous rate of change because the points are just so close together. So how do we notate this with our slope form? So what we do is we actually take the limit, it's a little cramped. So we take the limit of, as h goes to 0, of the slope formula. Again, what that does is it shrinks h to the point where we have 2 points that are basically side by side, A and another point, and they're so close together that we have the instantaneous rate of change, which is the derivative, and it's the slope of the tangent line at that point A. Okay, so I've written down what we know so far. We have this limit. We call this the limit definition of a derivative. So what we're going to use to find the derivative of a graph at a certain point x, or a certain x value. Let's do an example real quick with x squared. So f of x is x squared. So let's do our limit. So h goes to 0 of, so imagine we plug x plus h in for x. What do we get? X plus h squared. We plug in x, that's our input for x. We get x squared over just h. We can expand this to x squared plus 2xh plus h squared minus x squared all over h. X squareds cancel out. We're left with 2xh plus h squared over h. Okay. You can simplify even further. I can factor an h out. You're left with this. H's cancel out. And we have the limit as h approaches 0, 2x plus h. So how do we evaluate this limit? Well, we could just plug in 0 for h. We get 2x. So how do we, what's our notation for this? So basically, if we have the function f of x, the derivative of f of x, derivative of f of x is what we call f prime of x with this apostrophe. Apologize, it looks like a p. F prime of x. So in this example, f prime of x equals 2x. Now let's quickly evaluate this at a certain point. So let's say we have 0.24. I want to find the slope of this tangent line. What do? I plug 2 in for x. So f prime of 2, 2 is our input, is 2 times 2, which is 4. So basically this means the slope of f of x equals x squared at x equals 2 is equal to 4. The slope of the tangent line is 4. So we can use this for any point along our curve on any graph. That's the use of derivatives. We can call it the instantaneous rate of change. We can call it the slope formula. There's many names for it. We just need to understand that it's telling us the slope of a tangent line at a certain point on our graph. I hope you found something useful in this video and you learned. And please let me know if you have any recommendations in the comments or anything you want me to go over. Thank you.